Hello everyone, welcome to Engineering Archives. Let us look at our first learning problem for the chapter Cartesian vectors. So here we have the question, and this question is pretty simple. All it asks us to find are the angles that this force vector right here makes with the positive x, y, and z axes. So all we have to do is find the angles. You have to find this angle. We have to find this angle. We have to find this angle. And also we have to find this angle. Okay, so let me first write down the formula that we will use, and this formula is a very useful formula that we will also be using in other questions relating to this topic. So the formula says that I'm going to write down three formulas. First of all, the formula for a unit vector. So a unit vector in any direction is equal to the vector itself. Let's say the vector is called A, divided by magnitude of the vector A, right? Also, the second formula that we need to know is cos of an angle that a vector makes with any positive axis, let's say theta, is equal to the vector A, the component of the vector in direction of that axis divided by the magnitude of the vector. Okay, and this is theta x. The angle that the vector makes with the positive x-axis is equal to the component, the magnitude of the component along the x-axis divided by the magnitude of the vector. So I'm going to use this formula, and then you'll get to know this formula more closely. So let's just work with these two formulas for now. Okay, so let's get started. So the first angle that I'm going to find is my angle for theta z, or the angle that the vector makes with the positive z-axis. Okay, so according to this formula, cos of theta z should be equal to the component of the 75-pound force along the z-axis divided by magnitude of the force, which is 75 pounds. Okay, so so what I need right now is AZ, or the component along the z-axis, and we can find AZ simply by using the trigonometric identities for cos and sine theta. So we know that this is a right triangle right here. So we can simply do 75 sine of 30 degrees, and this would be equal to for AZ. But also notice that this component would be directed in the downwards direction. Since this is our triangle, our component would be in the downwards direction. So we have to put a negative sign. Okay, so now that we have AZ, we can solve for theta z. Substitute AZ into the equation, and we get negative 75 sine of 30 divided by 75. So after taking cos inverse of this, we get theta z equals to 120 degrees. The reason why I did theta z first was because we can actually find theta z without doing any of this procedure by simply looking at the diagram, and we see that this angle right here is 30 degrees, which means this angle that this vector makes with the negative z-axis should be 60 degrees. Similarly, if we add 30 degrees to 90 degrees, then we get 120 degrees for this angle. Okay, so let's move on to find theta x. So let's write down the formula first. Okay, so now we need AX, or the component of the 75-pound force along the x-axis. So right now I'm going to use a procedure that you might not have seen before. I'm going to use the trigonometric identity twice. First, I'm going to find the component of the 75-pound force along this line. And once I have this component, I'm going to use the trigonometric identity for sine once more to find my component along this x-axis. So first of all, I'm going to do 75 cos of 30 degrees. Now since I have put a cos of 30 degrees, the component that I should be getting is this component along this line, this component, right? But I need this component. So once I have this component, I can use this triangle to find this component. Okay, so once I have put cos of 30, I will add to that multiplied by sine of 45. Why did I do sine of 45? Because this is 90 degrees and this angle is 45. So by doing sine of 45, I got my component along the x-axis, right? I could have also done cos of 45 since this angle, this acute angle inside this triangle is also 45 degrees, and by doing cos of 45, I would also have got the same component along the x-axis. So once we solve for this, the value that we get is 45.93 pounds. Now that we have our component along the x-axis, we can solve for theta x by simply substituting in the value for ax. 75, and we get 52.2 degrees. Right. Now repeating the same procedure for theta y, you get cos of theta y should be equal to a y divided by 75, and then ay should be equal to 75. First of all, we find the component of this force along this line, and then we use this triangle to find the component along this line. So using this triangle first, we do 75 cos of 30 degrees to get this component. So we do 75 cos of 30 degrees. Now that we have this length right here, we will simply do cos of 45 to get this length using this right angle triangle. Cos of 45. And the answer that we get is 45.93. And substituting this into the formula, we get theta y is equal to cos inverse 45.93 over 75, and this gives us 52.2 degrees. So this is how we find the angles that the vector makes with each angle, with each axis. It's a pretty simple procedure, but the way to perfect this procedure is obviously practice. So practice a lot. Thank you very much. See you in the next video.